Hello friends, welcome to another tutorial in network analysis and synthesis. This is going to be a super interesting tutorial where I am going to compare all the 5 network solving techniques to solve a network, and this is going to be an ultimate comparison, and I'll leave it up to you to decide which technique do you like the most and which technique did you find the least cumbersome or the quickest. So let's get straight into it. We know that if we've been given with a network, we can solve that network using these 5 techniques: superposition theorem, KCL, which is nodal analysis, KVL, which is mesh analysis, Thevenin's theorem, and Norton's theorem. Now the biggest question is to decide which one to use when. So let's see, we've been given this network, so we'll keep this network the same, and we'll apply these 5 techniques on this network to solve the question here, which is to find the current through this 140 ohm resistor. Now please understand, the prerequisite of this video is the basic understanding of all the 5 techniques, because I'll not explain the details of how these techniques are applied. I'm simply going to apply these techniques. So when we apply superposition theorem, we take one source at a time and 3 sources, 2 voltage sources and 1 current source, and we'll take this voltage source first and we'll eliminate the other 2 sources, and the elimination happens by short circuiting the voltage sources and open circuiting the current sources. So this is what happens when superposition theorem is applied. First, let's take 480 volt voltage source. So this current source is open, this voltage source is shorted. Because of shorting this voltage source, this goes away, because this resistor is parallel to a shorted line, so this goes away. So what we are left with is just this circuit with 480 volts in series with 2 resistances, and the current through this 140 ohm will be the same, which is the series current, and I label it as I dash. So that becomes 2 ohms. So next I'll take the 12 ampere source. When I take 12 ampere source, this 480 volt voltage source goes away, it is shorted. 720 goes away, it is shorted, and the resistance parallel to that goes away because of this shorted line. And simply we need to calculate I double dash, which is the current through 140 ohm resistor. I double dash comes out to be, by the way, this is the current division rule. So if you have any problem in current division rule, you could watch my video on current division rule. So that simply states that the total current entering the node, which is 12, into opposite branches resistance 100 upon 100 plus 140 will give me the branch in my current. So it comes out to be 5 ampere. Now please understand, I've mentioned the direction of the currents in each of the case that I take up. In the last voltage source, I take 720 volt and I eliminate 12 ampere current source and the 480 volt voltage source. Of course, I need to find I triple dash, which can be found by simply applying Ohm's law on these parallel current through this branch. Parallel branch will be simply voltage upon resistance, and that comes out to be 3 amperes. And the direction of that current is in the opposite direction to the previous ones. So the total current becomes I dash plus I double dash plus I triple dash, which is 2 plus 5 minus 3, because it is algebraic sum, and that comes out to be 4 ampere. So the first technique is pretty simple, and it has quickly given me the answer. Now let's jump to the next technique, which is mesh analysis. Now please understand, in mesh analysis we'll take up loop currents in each of the loops, and because we have a current source in this branch, so it is not possible to determine the voltage drop here. So what I'll do is I'll take up this super mesh, and by analysis, because this current source is 12 ampere, I'll also get the relation between I1 and I2, and then I'll take up this last loop to find out 3 equations. So by inspection we know that I1 minus I2 is 12 ampere, so the sum total of this branch is 12, and by inspection we know that I1 and I2 are flowing in the opposite direction, so it is going to be I1 minus I2 is equal to 12 ampere, and you must take care of the directions. And in the third loop, which is the smallest loop, we know that when we move around this loop we see 720 volts and then some resistance, and some voltage is dropped across that resistance, which is 150 I3, and it is equivalent to 0. So this mesh gives me this equation, and the super mesh here gives me 480 minus 100 I1. I1 flows through this, I2 flows through this, and I3 flows through this, so I get this equation. And by the way, we need to find out I2, because I2 is the current which will flow in the 140 ohm resistor, and by solving 1, 2 and 3 we see that I2 is 4 ampere, which is the same current that we found using superposition theorem. And you could solve these equations in 3 variables using a 991 ES calculator, and done a separate video on how to do that. You could see that. So mesh analysis was also pretty simple. You need to simply take care of the fact that by inspection you've gotten some simpler equations. And next let's get to nodal analysis. Nodal analysis will assume some voltages across these two nodes, VA and VB, and please understand, by inspection we see that VB is equal to 720 volts, and if I assume currents in all the branches, which I can conveniently assume as I1 flowing in this branch, by the way I2 is simply 12 ampere by inspection, I3 is something that we need to find out. So this is something that we are striving to find out. I5 is the current in this branch, I4 is the current in this branch, but we are not concerned about finding these two. So what happens is I1 is the current in this branch, and of course the current will flow from we've assumed that the direction of flow of the current is this, so what we see is we start from 0 and then 480 is added because we are going from negative to positive, and then minus VA upon resistance. So current is expressed in terms of voltage upon resistance, 480 minus VA upon 100. I2 is 12 by inspection. I3 is VA minus VB, starting voltage minus the end voltage upon resistance, again V by R. I4 is VB by 150, and I5 is we really not bothered about finding I5 because VB is known to us. And the nodal analysis is based upon the Kirchhoff's current law, and at this node and this particular node we see that the incoming total current is I1 plus I2, and which is equivalent to I3, and we are concerned about finding I3 by the way, and I1 is nothing but 480 minus VA upon 100 plus 12, and I3 is VA minus 720 upon 140. Now, as I mentioned earlier, VB is 720 by inspection. So simply solving this equation, I get VA to be is equivalent to 1280. The voltage at this point is 1280. The voltage at this point is 720. So essentially, higher voltage, lower voltage, the direction of current will be this. And I3, which we need to find, is the voltage difference upon resistance. So VA is 1280, VB is 720 upon 140 gives me 4 amperes current, which is the same current, of course, in this direction that we found using the previous two techniques. So nodal analysis was also pretty simple. And let's get to the next theorem, which is the Thevenin's theorem. In Thevenin's theorem, a little bit of introduction. We find out the Thevenin's equivalent resistance. We find out the Thevenin's equivalent voltage. Thevenin's equivalent resistance is found by opening the terminals where the load is connected and removing all the sources. And the Thevenin's equivalent voltage is found using the open circuit voltage of this load, of course, by including the entire network. And finally, once we have found these two parameters, we simply use these two parameters in series with the load. So we take up VTH, we take up RTH, and we connect the load here. So this becomes a simpler network, and we find the current through that load. So the idea of using Thevenin's theorem is to reduce this complicated network into a simpler series network. So that is why we need to find out RTH and we need to find out VTH. For RTH, we remove all the sources. And how do we remove those sources? We short circuit the voltage sources and we open circuit the current sources, and we calculate the total equivalent resistance as seen from the load. So this was our load, 140 ohm load. We've removed that, and as seen from that load, I can see it's just the 100 ohm resistance. Because of this shorted path, this also goes away. So finding RTH was pretty simple in this case, but let's see what do we have for VTH. For VTH, we simply remove the load and we calculate this open voltage. VOC is also open circuit voltage across the load. So the voltage across this open circuit load is this voltage minus this voltage, as you can see. So this voltage is known to us because by inspection this voltage here is 720 ohms. If we consider this ground, so this point is at 720 ohms. And finding the voltage at this point is also not very difficult, because this current is given, 12 ampere current is flowing in this branch. So when 12 ampere current flows in this branch, of course it goes from a higher potential to lower potential, and it drops a voltage of 1200 volts across this resistance, because V is equal to IR. So this 12 ampere current flowing through this resistance will drop me a voltage of 1200 volt. Now one important thing that you can notice here is that these two voltage drops are in series, because you find a negative positive and a negative positive, so they'll be added. So this was one key point in this question, that when we find voltage drop across 100 ohm resistors, that comes out to be 1200, and Vx, I've assumed the voltage at point X to be Vx, and that becomes the sum total of these two voltages, 480 volts plus 1200 volts, which is dropped here. So my VTH becomes 1680 minus 720, which is 960, because VTH was the open circuit voltage across load. So this was 1680, which is the total voltage here. 1680 is the total voltage here, 720 is the total voltage here. So the VTH becomes 960, and I can put this VTH in my Thevenin's equivalent circuit, which is a simple series circuit. VTH in series with RTH and RL. So if I put 960 here, and 100 ohms here, and RL to be 140, my load resistance was 140. So what I get is, so the current through this series circuit is 960 divided by 240, which is 4 ampere. And so far we've consistently gotten the same result without any problem using all the 4 techniques. So let's go on with the last one, which is the Norton's theorem. Let's apply Norton's theorem to find out the current in the load. Please understand, Norton's theorem is reducing the network into a simpler network with just one current source, and it is in parallel to Norton's equivalent resistance and load. So the equivalent circuit for a Norton's equivalent theorem will be something like this, and we can simply calculate the load current. If this be the load current, this will be the total current entering the node, IN, into opposite branches resistance, RN upon RN plus RL. So main task is to find out RN and IN. So how do we find RN? The method is the same from the main circuit as we calculated RTH. So calculation of RTH and RN is the same, and calculation of IN is different. We, instead of open circuiting the load, we short circuit the load in this case. So in order to find IN, what I do is I short circuit the load, and my load was connected here, 140 ohms load was connected here. So if I can find this current, I'll be able to find out the value of IN that I need to put here. And so this circuit looks more or less like a problem of KVL. If I take up loop currents here, I1 and I2 and I3, my I2 will be equivalent to IN. So over here I'd like to make a special comment that while using Norton's theorem, you'll need to find out IN, and IN requires you to again use KVL within itself to find out IN. So this part is a little troublesome, or this could be a little lengthy. So but nevertheless we have to find that out. So in the first two loops, we see that I1 minus I2 is minus 12 by inspection, and in this super mesh we see that 480 minus 100 I1. So some voltage 100 I1 is dropped here, and some voltage 150 I3 is dropped here. Nothing gets dropped here, by the way. So we get this equation as number 2. And in loop 3, of course, we see that 720 minus 150 I3 is 0. And solving 1, 2 and 3, I get I2, this current I2, to be equivalent to 48 divided by 5. So you can solve these 3 equations using calculator. You will see that your I2 will be 48 divided by 5. So I have a source of 48 by 5 amperes, and I have a equivalent resistance of 100 ohms as calculated from RTH, and RL is 140 ohms. Now substituting these values here, let's see, I get the total current into opposite branches resistance upon opposite branches resistance plus my resistance, simply the current division rule, and that gives me an answer 4. So Norton theorem also gives me the same answer. As you can see, we've calculated the current in 140 ohms resistance branch using 5 different techniques comprehensively, and this could be thought of as an ultimate comparison between all the techniques. Which one do you think is the most efficient, and which one do you think is the most quickest and requires least effort? You could comment that in the comment section. And I hope this tutorial was interesting and was of help. If you liked the video, give it a thumbs up. Consider subscribing to my channel. I'll see you around in the next video. Take care. You have a great life ahead. Bye.